All right, so we've had our first exposure to solving a Newton's second law problem, but we're actually going to backtrack a little bit now and make sure that we can properly set up all the problems. So, and we did the same thing last unit where we started the unit by drawing all these real pictorial representations of problems, and then we simplified it with the particle model. And we're going to do the same thing with forces right now. And we started by taking a look at a physical situation and drawing or explaining all the forces that were interacting. And now we're going to simplify it up by drawing a free body diagram and talk about those as a really quick way of explaining the forces acting on an object. So what are free body diagrams? They are the equivalency of a picture or a motion diagram that we did in kinematics, except now we're going to apply forces. And these help us visualize the problem with all the forces, and most importantly, they don't just have all the forces, but they show the directions that the forces are acting. And when we've identified them so far, we've just kind of identified the fact that they're happening, and we haven't been drawing where and how they're happening, and that'll become extremely important as we try to go through and solve problems. So free body diagrams, it's a really quick way, a really easy way of visualizing forces. So here's how we make it. First, we identify all the forces that are acting on the object. We will establish a coordinate system. So we want to make sure we have X and Y directions, just as we did with projectile motion. It was extremely important to keep things in the X and the Y. Well, now we can take a look at acceleration in both directions a different way, and we got to make sure we have that correctly represented. We'll represent the object itself. It doesn't matter if it's a person or a thing, as a single dot at the origin. So to kind of sum up what we've done so far, we identify the forces. We're gonna draw a coordinate system, and right at the center of the coordinate system, that's going to be our object, just as a dot. Okay, and then as we get the different vectors or the different forces that pop up, we're going to draw each of them. We represent each of the identified forces, and so for example, if I know that there's the force of gravity, well, gravity pulls straight down, so I do the force of gravity. If there's the normal force goes straight up, so I do the normal force, and I just identify all of the forces acting. Let's say that the object is moving to the right, and there's a friction force opposing the motion. I will draw an arrow to the left. And then the very last thing that we're going to do is we're going to take a look at the net force vector. And the net force vector isn't a force vector, but it is something we want to consider. The net force points in the direction of the acceleration. So on my free body diagram here, I have a net force going to the left. And so what I do is right above, wherever I find a nice space, I put an arrow going to the left, and I label that up here as F net. So I do know that there is a net force. It is moving to the left because I have unbalanced forces. So this is a Newton's second law problem, which we'll talk more about as we start to quantify, but there is a net force going to the left, which means that there is also an acceleration also going to the left. All right, so we have an example problem now, and it's a very simple example problem. We have a book is lying at rest on a tabletop, draw forces acting on the book. So when I identify the forces, well, almost always there's going to be a weight force pulling down on the book, and in this case it's sitting on a table, so I know that there's a normal force as well. I draw the coordinate system, and this gets a little overkill. We don't need to really do this every time. I'm going to just draw it as like a dotted line, so that it's not as dark and heavy. And I'm gonna in black now. I'm gonna draw my object as a dot at the center of the origin. Those are my only two forces. My weight force goes straight down. My normal force goes straight up. Now, the length of these arrows absolutely matters, and because although this is just a visual representation, again, I should be able to get a lot of information from this. Now, if I look at a book sitting on a table, I know that it's not accelerating up or down, but I should be able to also tell that from my free body diagram. So, because the last step is what direction is the net force? Well, in this case, F net equals 0. There is no net force. This is what we call an equilibrium problem, where the object is not accelerating. So if it's sitting on a table, obviously it's not accelerating. So the forces need to be balanced. And we will talk about more about that in the next chapter. Here's another example. We have an egg is free falling from rest in a tree. Neglect air resistance, draw a diagram of the forces. So if I think about what forces are acting, I know I have weight. Weight is almost always a given. And as I think through this, I can't think of anything else that's actually acting. There's no drag force because there's no air resistance. And actually that ends up being 100% correct, that we think about this as an object in free fall. Well, an object in free fall and a projectile have the same kind of characteristics, that a projectile is an object that moves through the air, in which the only force acting on it is gravity. So in this case, F net is straight down. We just have the weight force going down, and that is, in this case, actually equal to the net force. And we'll talk more about these when we get into solving problems. All right, another example. Now we have a skydiver is descending with constant velocity. And it also follows it up by saying consider air resistance. So if I think about that, a skydiver has to have a weight force acting on them because gravity is pulling them down. And in this case, if I am considering air resistance, which I have to if I know that we're in free fall but with constant velocity, that means that there's a drag force pushing back up on me. And I'm going to simplify this one, and I'm just going to go ahead and say that I'm going to skip my coordinate system. My weight is going straight down. My drag force is going straight up. And if I did this right, F net should be equal to 0, because if I'm descending with a constant velocity, as said right there, that means that my acceleration has to be equal to 0, which means my net force has to be equal to 0. So we'll start to see these patterns as we get into problem solving in Chapter 5. All right, another example problem. A car is coasting to the right and slowing down. Neglect air resistance, draw a diagram of the forces. So if we identify it, of course we will have a weight force. That should always be a given. If the car is not accelerating up or down, then there is a normal force, and spoiler alert, that should be equal and opposite to the car's weight. And if I'm going to the right but slowing down, that means I got some type of friction that is causing me to slow down. In this case, this is the friction of motion, so we'll call that kinetic friction. And the question is, what is the force going the opposite of the friction? And the answer is there isn't one. So let me show you what I mean when I draw a free body diagram. Okay, so here's my dot, my particle. The weight is straight down. The normal force is straight up. And it's moving to the right, but it's slowing down, which means that there's friction opposing motion. I'm going to put that right there, the force of kinetic friction. Kinetic, of course, meaning in motion. And my question I'm asking is, what should be going to the right? So the car is moving to the right. The direction of motion is to the right, but there is no force acting to the right. This is actually complete. My free body diagram that I have right here is all done. The net force, of course, going to the left in the direction of the friction. There is no force going to the right. So I mentioned this before, just because an object is in motion doesn't mean that there's a force keeping them in motion. In this case, there is no force going to the right. All right, got a quick check. So it says an elevator lifted by a cable is moving upward and slowing down. So if it's up, it's moving up, but it's slowing down. That means the acceleration has to be directed down. And if the acceleration is down because it's slowing down as it's going up in the positive direction, that means there must be a net force going down, which means that the force that's going up needs to be smaller than the force going down, and that's how we come up with C. So we have some type of force right here. It's this long. That's going up. That's the tension in the cable. And then we have a force that's this long, much longer, or at least a little bit longer, and that's the weight force. So as you're going up, slowing down, the weight force is larger, and that's what's causing that negative acceleration. Got another quick check. It says a ball has been tossed straight up, which is the correct free body diagram. And of course, we always have to think about just after the ball has left the hand. And in that case, it's actually in free fall. So the only force acting on it is gravity, which means that the only force acting is straight down. And we get D as our correct answer. All right, another quick check problem. We have a car is parked on a hill. What's the correct free body diagram? Well, if I quick identify, I'll have the weight force, I'll have a normal force, and I'll have, because it's parked on the hill but not moving, there's some type of static friction, and we'll talk more about that when we get into friction next unit. Now, how we draw these is all of them are correct in that we have the this weight force that's going straight down. Gravity always acts straight down. Oh, wait. That's not right. D is not correct. D does not have gravity going straight down. D actually has some things that make sense because we know that the car is balanced, so it must be in equilibrium, meaning that all the forces are balanced. But what they did here is they broke this and this. These are the two components of gravity, so those are not correct. So D, we know, is not the correct answer as we go through this. Okay, then we also have the normal force, and the normal force is always perpendicular to the surface. So, and it's going straight up from the surface, so that's correct. C is still correct, B is still correct, and A is still correct. And that's where we kind of lose E, is E doesn't have that normal force identified, so that's not right. And finally, we have friction. And friction has to be opposing the motion, which we get in C. So gravity wants to pull it down the hill, and the friction is keeping it up the hill from the brakes or from the parking brake on the car, which makes C our correct answer. So C itself is the correct answer. Now, this might look a little weird, but the reason it works is that there's an X component. If I look at my force of gravity right here, there's an X component and there's a Y component, and those two need to be balanced out. So the X component is balanced out by friction, and the Y component is, the Y component is balanced out by the normal force, and that's what keeps this one all balanced. All right, so you got a partner problem that you should try setting up with your partner, and I'll just kind of walk you through it a little bit. And it says, consider pushing a block across the table at a steady speed. And of course, anytime we say steady speed, we know that that means acceleration equals 0. We'll actually do a lab on pushing and pulling blocks a little bit later. Since you're exerting a force on it, why isn't it accelerating? Think about why it's not accelerating. And you can do that by identifying all the forces and draw a free body diagram. So go through and don't forget to compare the magnitudes of each of the forces. Hint, if acceleration is 0, what should my net force be? Also 0. So make sure as you're drawing the free body diagram that you go ahead and have a net force that is equal to 0. And we'll talk about this one in class. And that will actually conclude this part of free body diagrams. And we'll continue with Newton's third law in the next segment and close out this introduction chapter and then get into actual problem solving in chapter 5.